So let me go ahead and introduce Dr. Drager. Go ahead. Can you turn to the next page? Okay, so one thing I did was I did a quick review on Lam Research. I was very surprised. Actually, it's founded in 1980 and by Dr. Actually David Lam. Is that right? And I mean, they almost double their revenue every year and they come to 5.3 billion. I think maybe now it's even higher. I didn't check on the stock, how things are doing with some. But anyway, it's a very huge equipment supplier. So if you know the semiconductor chain, actually there's manufacturing, more like a foundry level, and the chip design or software developer. And we also have a very important component, which is the equipment supplier. And so Lam Research kicking in that direction. I downloaded some of the front page of their products. Primarily, they do thin film tools in variety of almost any material you can find in semiconductor industry. You can find the tools to manufacture that. The second half is actually their specialty on etching. So etching is one of the many very important components for the IC fabrication. Last one is cleaning. So you will know actually how important the cleaning is. I think Dr. Drager going to give you some information on that. So last page. Okay, so this is about the highlight page. I cannot read more than enough about her background. Actually, she graduated from UIUC with a PhD in thin film, in material science, but they're on thin film. And then she joined, actually, the company originally, not Lam Research. What was the company?
Novellus Systems, which is another equipment company.
Yes, specializing in thin film. Later on, being acquired by Lam Research. So that's why she's in Lam Research. And she's now the senior innovation leader in the CTO office for Lam Research. CTO, I believe it's called the Chief Technology Office, is that right? For developing new advanced innovation in the company. And then her actually research, interest lies in the intersection of emerging technology, strategy, and people. And then she's leading on the university engagement. That's why she's here representing Lam Research. And I also want to highlight a few things. She's very outreach. I joined the same panel as her working in the MIS and also a big driver in terms of many industrial director, board of director role, advisory roles, just very outreach. So let's hear what she will say today. Okay, great. Thank you. Yeah,
thank you. Yeah. Well, I'm looking forward to speaking to all of you because I believe most of you are freshmen. Is that okay? Nodding heads. Great. So you don't yet maybe know what you want to major in or what you want to do. So this is a perfect time to hear about semiconductors. I'm glad you're in the class. And what I'm going to show you actually requires engineers from all different disciplines for our company. So there's a lot of different majors that you could move into and still work in a company like Lam Research in the semiconductor industry. Okay. It's not showing on the screen. I hate to keep looking over my shoulder to see what's up, so let me see if I can get it projected here as well. Okay, that's all right. I will stand off to the side so I can see it then. So just a little bit about who I am. I've been in the industry for a while. I'm a materials engineering by training, specifically in thin film deposition. Thank you. For electronic materials. As Hyen introduced, I work in the office of the CTO and I oversee how Lam works as a company with universities on advanced research. A lot of the technologies that come into the semiconductor industry are developed in universities first. So things like if you've heard about the FinFET, which is the standard transistor from Intel, developed at UC Berkeley. A lot of the other device types are coming out of universities. So we like to work with universities, students, and faculty around some of these neat technologies that are coming. And do a lot of things in my free time, traveler, hiker, have 2 cats and a dog at the moment. So a little bit about it's changing on the screen on my laptop, but not down here. Oops. moving on the screen, but not down.
Oh, maybe there's a delay. Now
Okay.
Yes,
All right. So maybe just a little bit of what my career journey has been, just to give you an example, of the industry. So, majored in material science and engineering for both undergraduate and my PhD. I'm a native Midwesterner, so I did them locally. Grew up in Michigan, did undergrad at University of Michigan. Sorry, still have a sports alliance there. And PhD at University of Illinois, just a few hours away, and then joined a company called Develop Systems as a process engineer. So developing the processes that make new materials and chips, ultimately. And from there, did a lot of new product development. So when you're doing R&D, you test a bunch of ideas. If they're successful in the lab, you want to make a product and you want to sell them. So we would do that. Sometimes those products succeed and then they move on and we place them with a customer. And our customers, I'll explain more later, are people that operate the chip fabs. Sometimes they don't work, you shelve them and you go back in any case and do a new idea. So go through several cycles of that. And then I wanted to do something a little bit different and moved into more of a business role, doing strategic business development and intellectual property development. Learned a lot there about how companies can manage innovation, but ultimately I like the technology. I'm an engineer, so I went back into a product group. And then we were acquired by the company Lam Research and moved into the office of the CTO, leading some early technology development groups, and now into the role that I do right now. So it's a little bit of, when you draw these career lines, they always look like straight lines. They're not straight lines. They never are. It's actually a bit of a curvy line. So another timeline on pace of innovation. If you think about the big innovations that have changed the world, the printing press, the telescope, steam engines, Boilermakers, light bulb, and all the technologies now, if you plot that out, so many innovations have really occurred within the last 100 years. Anything electronic, all of the internet. So, the pace of innovation is accelerating because you're building on previous technologies. And we think the pace will continue to accelerate. And along with that, semiconductor demand is also intensifying. It used to be decades ago, it was just computers, and then just computers and mobile, and okay, then there's data centers. Now it's in everything. My dryer can text me when it's done with a load, the refrigerator's connected to the internet, your car is filled with electronics. Car lines were idle during the first part of the pandemic just because shortage of chips. And not expensive high-end chips. The shortage of chips that they had were ones that are costing a few dollars. These are not expensive systems necessarily that are needed. They're not the same thing that are running high-performance computers. So all of this is accelerating and it's increasing as well. And the semiconductor industry is expected to hit the $1 trillion mark in maybe 2030. That's not that far away. But it's an industry that needs new innovations and technology development to be able to get there. So it's a fun industry to work in because we're always reinventing what the technology is. So there's always new innovations, new problems to solve. And behind all of those chips and electronics, there are going to be Lam products that are used to make them. So our role in the industry is a semiconductor equipment maker. We make the equipment, and that's an example right there. That's a big piece of equipment, maybe like, the size of like a restaurant walk-in freezer. Larger than any one of these tables that you're sitting at. And it's used to deposit, etch, clean, the various layers that are used to build up a chip. But not only do we make the equipment, we model and develop the processes that that equipment performs that are used to make the chip, the materials and the etching processes. And just because you can design something doesn't mean that you can make it. So that's an important caveat. And so that's why the modeling is very important, because you can actually model what the fabrication flow is going to be like to see, can you actually make this in reality once you go into the fab. So we're up to $19 billion revenue as a company, about 19,000 employees worldwide. We're headquartered in Silicon Valley and have an equally large office in the Portland, Oregon area. And those are our two biggest locations in the US. But anywhere where there is a customer and a fab, then we have an office to support our customers and the tools that we have in those fabs as well. So you can see we have a lot of locations around the world as well. So you've already in your class seen kind of an introduction to semiconductor fabrication. And you know there's about 700 processing steps to get to the end of a chip. I mean, dozens of layers of patterns that are printed, deposited, etched. And Lam is involved in many of those steps. And equipments like us, we're not the only semiconductor equipment company. Applied Materials, Tokyo Electron, ASM, or other equipment companies that operate similar spaces. In some cases, we might be competitors. In some cases, we might, KLA is another equipment company, but they're all around characterization equipment, so they're just peers. We don't compete. But there's really 5 large equipment companies in the world today in the industry. And 3 of them are still based in the US. So the role that Lam plays in the wafer fabrication, so this is a really rough schematic. If that gray bar there at the bottom is a silicon wafer, and most of the industry is 300 millimeters right now, so 12 inches, it's like the size of a large pizza. You can think of that's the size of the wafers. We do a lot of deposition of thin films. So you can think of really roughly, you deposit a film, and chips are ultimately 3-dimensional structures. So that has to be patterned. So it'll go through extreme UV exposure is currently the industry standard. It can print down to, let's say, around 10 to 13 nanometers. You expose a photoresist. The part, it can be positive or negative, so you can either remove the part that gets exposed, or the opposite, you remove the part that doesn't get exposed. And now you've got a mask, essentially. And then you etch where that material's been exposed to remove it. So now you have a 3-dimensional structure. You strip to remove that photoresist and any extra masking layers you might have used. And then you have to clean it to remove the residue from all of those processes. So all of those, the deposition, we offer resist that's used in the patterning, etch, strip, and clean are all products that Lam designs and sells to our customers in the fab. And then you repeat that. So that gets repeated to make up the 700 steps. You know, the next layer comes down and you go with your next level of materials. So what do we need? What skills do we need and expertise to be able to do that? We kind of break them down into 4 categories. There's what we would call the on-wafer process. That's a lot of chemistry, chemical engineering, materials engineering. It's understanding the surfaces and the interfaces. And we sell the equipment too. So there's an awful lot of, we call them subsystems, but we're thinking about mechanical, electrical, radio frequency plasma subsystems that go into there. You have to control pressures and temperatures, and you've got all of the circular chemical energy waste management. A lot of the materials that we develop in the processes use plasma in them. So there's a lot of really high-tech plasma systems that go into it. Software and control. Okay, so we have the software that runs the tools for sure, but we have a lot of algorithms and analytics that go into monitoring the tool performance in the fab. You know, you can do predictive, preventative maintenance in there. We do modeling and simulation internally to the company, so we hire a lot of modelers in that space. And then, you know, the sensors and the timing, all the UX. So that's all done internally to the company. And the last you think of is kind of the grander system. So now that's a picture of one of the tools right there. We need mechatronics. We need automation, development of the architecture. You know, there's robotics and the mechatronics that handle all the wafers and move them around. So we need all of these disciplines as a company to be able to deliver our technology. So that's, you know, what I mean. If no matter kind of really almost what major you end up going into, you know, there could potentially be a role for you in the semiconductor industry. So the next part of my talk, I'm going to look at just a few examples of what we call grand challenges. So across the company, what do we need to achieve next generation technologies for the chips? Atomic scale precision, we mean that literally. Affordability, because this is an industry that has to sell products to make money. So affordability is there. Sustainability, certainly to address this in industry to make sure we're minimizing impact on the climate. And speed to solution. That gets back to that pace of technology is accelerating. So the first one I'm going to look at is atomic scale precision and give you an example. So if you think of a continuous film deposition process, and this is going to be a basic schematic, and I'm giving you an example for a plasma-enhanced chemical vapor deposition. That gray box there is a vacuum chamber. Maybe it's operating at, it could be operating from like 5 millitorr to like 1 torr. Room pressure is 760 torr. So you need a shower head, and a shower head delivers reactants to the wafer. We call it a shower head because it does essentially the same thing as the shower head in your shower, which delivers water, but ours is delivering reactant chemicals. But it's, round piece, many holes. You've got a wafer, and you supply a reactive gas mix into the chamber, and you supply energy for the reaction, and that is often either temperature or a plasma in the chamber. And that creates the energy that the chemical reaction needs to take place then. So you got your reaction and you build up your film. And that's done continuously where everything is at the same time. If you, an example, silane plus ammonia, you're going to give you a silicon nitride film. So the reverse process is that if you want to look at an etch process, reactive ion etch is kind of the traditional product for Lam initially, and also a standard for the industry. Again, you've got a vacuum chamber. Same sort of thing, that you have a top electrode for the plasma, and the white bit or the holes from the shower head, that's where the gases are going to come in. You have your wafer, but this time you've already got a film and a pattern on top of it. And the film is what we want to remove. The green layer and the brown one is what we would call an etch mask. We don't want to remove the film that's under that mask. So you supply, your reactive gas mixtures again. It's a plasma process, so you're generating reactive species. And you've chosen the species in the etch mask that mask does not get etched, or it gets etched at a very low rate relative to the film, and you can remove the film. So a reverse example then is if you want to remove silicon dioxide, you can add CF4, you create a silicon fluoride compound, which is a gas, it's volatile, so it goes away from the surface, and CO2, which is a gas, and you remove the film. So, but those are continuous processes. And so you only have so much control over them. So products that Lam has introduced into the market for atomic scale precision, one of those grand challenges is atomic layer deposition and etch, and hopefully the audio works.
Following the trajectory of Moore's Law, the semiconductor industry has transitioned from microelectronics in the 1980s and nanoelectronics in the early 2000s to today, where we have entered an era of atomic scale dimensions. At the atomic scale, with only tens of atoms at stake, there is no margin for error. Every atom matters. Which is why developing the most advanced technology presents such an unprecedented challenge for chipmakers. Increasingly critical in the making of state-of-the-art semiconductor devices are deposition and etch processes, which involve gases or ions reacting directly with the wafer surface, often using plasma to make reactions faster. For decades, these processes have been performed by delivering all of the reactants to the wafer at the same time for the duration of the process. However, in the atomic era, these processes are increasingly difficult to control, and for the most advanced structures, they simply won't meet the requirements anymore. The breakthrough that was needed can be found in atomic scale processing, where we can achieve greater control by separating out the reaction steps. In atomic layer deposition, or ALD, 2 adsorption steps occur in sequence to produce a conformal film, even on high aspect ratio or 3-dimensional geometries. While multi-step processes tend to be slow, we can make them faster by quickly switching between the individual steps and using plasma. After many years in the laboratory, ALD has become productive enough to be a mainstream technology. However, the etch counterpart, Atomic layer etch, or ALE, has been much more challenging to bring from the lab to the fab. It turns out that it is much harder to atomically remove films than it is to deposit them, especially when you need to etch directionally. But at Lam Research, we found a way to make it happen. The ALE process is based on the same concept as ALD in that the reaction steps are separated. ALE typically starts with an adsorption step to form a reactive layer, followed by a removal step called desorption to take off this layer. Using ions allows for the directional etching required to form deep, narrow structures. One of the biggest challenges for ALE has been throughput, and this is where ALE benefits from having ALD as a predecessor. Fast switching between individual steps and the use of plasma are the keys to this process. Lam's patented first-generation ALE technology joins our existing portfolio of ALD tools today.
Okay. You don't need to hear the tool bit. That's just marketing for the customers. So, atomic layer processing gives us much greater control, atomic scale control, because you are depositing an atomic layer at a time, which originally was very slow. It was developed in the lab, actually at universities decades ago, but it took a long time to be able to speed it up to the point that it could be used in production for high volume manufacturing of semiconductors. So the difference between kind of a continuous process and the atomic layer is these steps are individually separated from each other. So for the deposition example, you bring in a silicon precursor. It's usually an organometallic. It's a silicon that's going to be bonded to, let's say, an amino group or some other labile, group with carbon, nitrogen, hydrogen. And in this example, you bring in an oxygen plasma that reacts and strips off that excess, but leaves only the silicon, and the oxygen bonds with that silicon to create your silicon dioxide. It's a similar in reverse for the atomic layer etch process. So if you want to remove silicon, you can bring in, say, a chlorine layer, and that can be as a gas or often as a plasma. And then you bombard it, in this case with argon ions. And you can think of ions from a plasma as mini cannonballs, that they physically strike the surface. They will have an energy greater than the binding energy of that atom to the surface, and they eject it. So you remove the reacted silicon bonded to the chloride, but not the silicon bonded to itself, the underlayer of silicon. So you have to control that energy very precisely. If it's too much, you just start etching continuously, and you've got reactive ion etch again. But if it's not enough, then you don't remove that layer. So the key is that they are separate steps, and they're self-limiting. So this is an example of the chlorine exposure time on the x-axis and the etch rate per cycle, per exposure, on the y. So you can keep exposing more chlorine for longer, but you're not going to remove any more film because it will saturate. And the same with the next step. It's the same etch per cycle now, but we're looking at the argon ion step time. And again, you can keep bombarding it with argon, but we've tuned in that energy level that will only remove what was reacted with chlorine. So when you remove that atomic layer, it just stops and nothing else gets removed. And this gives us really precise control and a lot of other advantages. So these are examples of looking, what do we gain? It's independent of what we call the aspect ratio. So if you're etching a feature, how far down is it compared to how wide it is? And aspect ratios of devices can be, at the low end, let's say 2:1, or if you're talking about flash memory, which is a 3D NAND device, those are 100:1. You have to get materials down to the bottom of something that's 100 times as deep as it is wide. That's basically the aspect ratio of the biggest skyscrapers in the world. It can give us really good uniformity across an entire 12-inch wafer and really good repeatability, the same from wafer to wafer. So these are real examples, like for the deposition, looking at that very middle graph there. If you're looking at, and that was a thicker film example, but if you're looking across an entire film, it's 1,200 angstroms thick, the variation had less than 0.15% variation on that. And the repeatability from wafer to wafer was less than 1 angstrom variation. So, that's the kind of precision that's required for high volume manufacturing and that we gain from these new techniques that we've developed and brought to market. So the next grand challenge I'm going to turn to then is one that's addressing affordability and speed to solution. So historically, we do process engineering in an Edisonian way, meaning like Thomas Edison did it. To get to the light bulb, he did somewhere between like 1,000 to 3,000 different experiments before he landed on a carbon filament. And that's the way that we used to do, and we still do in many cases, develop process engineering in the lab. So you make a hypothesis, you design your experiments, you run the experiments, look at the metrology, and then you keep iterating on that until you meet the specification. And the example I'll use for this grand challenge is doing a high aspect ratio etch. So we want the etched structure to look like that. The black bit is what we've removed. The gray bit is silicon that's left. So is there a better way to do this? So if you look at what process variables, if you walk up to one of our tools and you want to be doing that etch process, how many variables or different knobs do you have to control things? Okay, there's multiple pressures and powers, and you've got all the reactant gas flows, and it's a cycling process, so there's duty cycles and frequencies and temperatures. And what do we have to develop? Well, we have to know the etch depth and the rate, how much of that etch mask remains, what is the CD, which is the width, critical dimension is what it stands for, kind of at the top of the structure, at the bottom of the structure. And on the left, you can see, things that don't look the way we want. There's too much byproduct at the top and it blocked the etch, or we removed the mask and now we're etching everywhere. So you've got all these variables, and we've kind of coined this internally as Lamb's law. So the graph I'm showing you is you have many variables, which means there's many possible process recipes you could develop, but very little data available to develop all of those. So this is looking at on the left, the gray is Moore's law. You're scaling down the feature size of the chips, roughly by half every 2 years was the original Moore's Law prediction. And on the right is the number of possible recipe combinations you need to deliver that. And it's going up at the same time. So, there's trillions of possible recipe combinations. Any human is not going to get there from running a design of experiments with a lot of wafers. So, can we do this faster virtually? Can we develop process modeling that then even develops and predicts the processes? So we tried it. So we made up an experiment and basically said, for this case, we're going to assign a cost. Let's say it costs you $1,000 for every recipe that you want to try, $1,000 to run a batch of wafers to validate it, and you can only run one batch of wafers a day. So we built, we have physics-based models of our etch processes, and we map those to what we want to measure in the chamber and the output, the metrology parameters we want to have, and plug that into a machine learning model to try and develop the best process. And what we found is if you just give it raw into the algorithm, and remember we assigned it cost to running experiments, the algorithm was by far the most costly way to do it. It just did not get to solution. It ran a zillion recipes and batches. If you give it to an experienced process engineer, they did better than the algorithm did. We also did it where we gave it to people that weren't even engineers. We asked for volunteers throughout the company from like corporate communications and human resources. And we tested, when did we give it to the algorithm? When did we give it to the process engineer? And we found that there's a really good combination that was the most efficient at getting to a solution is if an experienced process engineer started first. They got it to kind of the right rough space and then fed it into the machine learning model. And the machine learning model would get it to the end result we desired faster than the process engineer would at that point. So it's a hybrid approach, human first and machine last. We can actually get there a lot faster than continuing to use the Edisonian approach from start to finish. And we have a science paper on this, and the link is in this. You'll get the slides so you can look it up, and I think it was in your pre-reading as well. So that was a really fun experiment we did to try and validate this. Now this is still in the experimental stage. The model can't develop every process recipe we need yet, but that's what we're moving towards. So we need folks in computer engineering and in machine learning and AI and analytics analytics as well in the company. They're the ones that are building these models. And the last grand challenge I want to talk about is sustainability. So if you're familiar maybe with how companies assess the emissions, there's different scopes. Scope 1 is what do we own? The labs we operate, our manufacturing facilities, and the energy and the water they use. Scope 2 is what are we purchasing? So, what was the emission? Where do we get our electricity from? Was it a coal-fired plant? Was it wind energy, renewable source? Scope 3 is when our products are used in the fabs by our customers, that's the emissions they generate. By far, Scope 3 is our largest. It's use of our products in the fabs that generate the most impact in greenhouse gas emissions and in CO2 equivalent production. And one of the biggest impacts is if you look at those reactive chemicals that we use in the industry, they are very high global warming potential gases. So you saw that, my example of wanting to etch silicon dioxide, use CF4. And there's a lot of other carbon fluoride or carbon chloride that are used for etching. NF3 nitrogen trifluoride is commonly used to clean the deposition chambers. Because anytime you deposit on a wafer, you're depositing on the entire inside of that reactor as well, and that material eventually needs to be cleaned off to be able to continue. So now not all of these are not released to the atmosphere. Fabs have abatement. They get treated at the fab sites so that they're not released, but that's expensive and costly. And it's not 100% efficient abatement. So this is a big opportunity for developing new chemistries. So we've been working on some new chemistries and this is new, so I can't tell you what the chemistries are, but we're working with our chemical suppliers to test new ones. And we have some examples of, this is an example of kind of pre-abatement in the fab and then post-abatement. On basically the equivalent of kilogram of CO2 released for our baseline process in gray and the new material in green. So it's a significant improvement on the amount of emissions that come from this. But this needs to be developed for all of the deposition and etch processes that we use in the company. So sustainability is a really big opportunity for improvement in the next few years, and there's going to be a lot of innovations that are coming out of this now. But that can't be done, by ourselves. The whole industry has to tackle it together. So we work with our customers, we're the ones operating the fabs, ourselves, our chemical suppliers, and in the overall innovation ecosystem. We work with universities on exploring some of these new chemistries and processes. So that is all of the kind of a quick, intro to some of the challenges that an equipment company looks at and what we do in the role. I don't want to go through these, but we're well regarded for not just the technology that we sell, but for how we operate as a company as well. And I wanted to talk a little bit just kind of about, recruiting, what careers would look like. So process engineers, product engineers are the biggest roles that we hire from. And if you look at the majors we recruit, there's a lot of them. I would say probably the top 4 that we hire in the company would be chemical engineering, chemistry, material science engineering, mechanical engineering, but there's a lot of others we need as well. And we have internship programs for all of this. That's available at bachelor's, master's, and PhD level at our facilities in California and Oregon. So, all of this is on our website if you're interested. And also wanted to let you know, for those who are not interested in the West Coast, we have a subsidiary of Lam called Silfex. It's based in Ohio, and they manufacture silicon. So silicon components for the semiconductor industry. So if you've ever seen the examples of like the single crystal silicon boules, they grow those. It's amazing to see. Really, really high tech and cool technology. So they're based in Ohio, and they have both internships and a co-op program as well. So since Purdue has a co-op program, that might be a good opportunity, and certainly hire full-time roles too. And they're their own independent subsidiary, so they have their own careers website under Silfex. And that's the end. I wanted to leave plenty of time for you to ask me questions. That's a QR code. If you do want to, get more information about internships or positions at Lam, you can bring that up and input your information that way as well. But I would love to hear your questions and what you want to know.
Yeah, great. Let's thank our speaker. Questions? So he picked for me. Okay, so I'm going to just run some of them, and if you come up with some new questions or interesting questions, do raise your hand. Okay, so some of the technical, oh, I'm sorry, I was speaking to the air. Okay, so technical questions. What are some of the challenges faced in developing semiconductor architecture, such as gate-all-around transistors? That's one of the questions for technical. Then besides the hybrid approach for chip design strategy, what are other process is AI used for? Could AI eventually take over the design process? Okay, that's actually two questions. Yeah, go ahead. Yes.
I'll answer the first one. Gate-all-around has introduced some really unique challenges. So it used to be, when you had a FinFET, think of it as like a high-rise, everything is, all those surfaces, the vertical sidewalls, the top surface, even the etch between, let's say, the fins above, it's line of sight to the reactor chamber. But all of a sudden, when you've now created gate-all-around, you have to etch and deposit in those lateral sections. So you've taken your high-rise, and now you've created individual layers, and those have to be completely surrounded. So the area in between these is not line of sight to the reactor. So you have to be able to get the chemistry, whether you're etching or depositing, in between those layers, but still control it at that same atomic layer precision. Plasma species don't do that very well. Plasma species, many of them really like to be line of sight. They have to see the surface that they're going to impinge with. Thermal processes that are controlled by heat, not plasma, don't have that limitation. So you need both plasma processes and thermal processes to be able to do gate-all-around.
I see.
Yeah. And on the second question, so Lam is not a design company, so I can't answer from the design perspective, but I gave you an example in the talk of how we're using AI and ML to help us with process development, to actually develop recipes. Another way we're using it is, when we have the tools in the fab, those have to be supported. Essentially you can think of it like an automobile at that point. Yeah. It needs regular maintenance and service, it's going to have parts wear out and need to be replaced. Well, all of these have sensors and measurements on everything. You can measure temperature variations, you can measure flow variations and mass flow controllers. Everything has a sensor. So there's huge amount of big data coming from every single tool in the fab and across a whole fleet of tools in the fab. But there aren't that many failures, so that's actually little data. So you have to solve a little data problem in kind of a big data environment. So we use AI/ML to help us analyze and understand what signals from the tool are important and what ones aren't. Because the goal is basically to be able to predict when something is starting to wear out and needs to be replaced. We call this equipment intelligence in the company, how we use it. And we've had an etch reactor that, when you etch the materials on the wafer, you're etching every single thing in the reactor as well. So you can address that by making sure you're using materials that don't etch very much, but there's always going to be some consumption. And the part that wears out the quickest is there's a ring around the wafer, and it basically helps control uniformity of the etch process, and that ring wears out pretty fast. So we designed a reactor that has all of these extra rings inside of it. And it's monitoring basically the signals in the chamber to know when that ring is wearing out. And it has the mechatronics, the robotics to basically just pull the ring and replace it. So that etch chamber ran in production in a customer fab for an entire year without having to be opened. So those of you who have ever worked on tools, and certainly your students would know, they usually require a lot of maintenance. So it's very impressive. Yeah, to never have to open it for an entire year in production. So that's another way that we use AI/ML. Yeah.
Great. I think as tool supplier, you will know customer service is very important. You want to buy the best tool in the market. Is that right? Okay, second set of questions is about the industry part. What do you see as the next big shift in semiconductor manufacturing technology? Oh, that's a very big question. We can answer that question.
Yeah.
But maybe from Lam Research perspective.
You know, from the industry as a whole and how we make chips, the industry is moving towards lights out fabs. You know, it used to be that people actually physically would carry, you know, these box of wafers. There's an industry standard. It's 25, you know, wafers in a box, you know, put it on the tool, and then the tool processes the wafers. That went away a long time ago. And now all the wafer boxes are actually moved by tracks on the ceilings of the fabs that drop them down onto the tools and collect them when they need to. Because humans are a great source of contamination. You know, I talked about atomic scale precision. You can't have any defects. You can't have any excess chemical contamination. And in a fab, most of those come from us. We sweat. That's chlorine. Chlorine's terrible to have exposed next to silicon-based electronics. You know, we have skin particles and hair particles that fall off, and that, you know, that's a lot of what creates a lot of the dust in our home. You certainly don't want that in a semiconductor fab. So removing the humans away from where the wafers are processed is the best thing you can do for eliminating some of those sources of contamination. So they're moving towards what they want to call as the lights out fab, that the humans aren't in the fab. On a regular basis. You know, they may need to for certain purposes. And that basically robotics are handling all the wafer movements already, but also all of the tool maintenance. If we need to replace a part, what parts can we do with robotics? And basically engineers are remotely controlling everything from outside the fab. They're still the engineers that are running everything and designing everything, but they're physically not in the bunny suits in the lab, but they're outside at their computers. So I think that change is going to be coming.
Great. Another one is, how is Lam Research navigating the challenging global semiconductor supply chain to meet the growing demand for more advanced, sustainable semiconductor technology? Oh, that's a very good question for CTO. Okay, go ahead.
Oh, yeah, we had our own supply chain issues during the first part of the pandemic too, and couldn't get the parts we needed to build our own equipment to get to customers. So, you know, at one point, I think it was maybe even the CEO or CTO of ASML, which is an equipment company that supplies the advanced lithography tools, you know, made a comment that they're buying old like washing machines and dishwashers to strip some of the base chips out of those, because those were things they couldn't get. I mean, you know, these are not the high-end stuff, but so we've dealt certainly with supply chain issues as well, and also you know, certainly geopolitical issues. You know, with the war between Russia and Ukraine, there are a lot of critical metals that are mined in Russia that aren't available for mining in many other places of the world. So things like that certainly make a difference. But yeah, it's, you know, we have a number of manufacturing facilities, in both California and Oregon, then also ones that are closer to our customers around the world as well. To make sure that we have, you know, capability, if we can't manufacture at one site, that we can switch and manufacture at another site, and just working with our suppliers to make sure there's a healthy supply chain.
Yeah, great, thank you. Okay, I want to leave the last few minutes to additional question from the audience. You know, you might have some additional question. Go ahead. You want to?
So you mentioned how Lam Research does the vast majority of the steps, or at least has a hand in the vast majority of the steps of making a
lot
semiconductor. Do you know if Lam has ever considered becoming a fab and just using your own machines to make semiconductors?
No. You know, the industry has gotten kind of specialized. That's how it started. Like back in its infancy in like the 60s and the 70s, like Fairchild Semiconductor and then Intel did everything. They made their own tools, they developed the materials and the processes, and they made the chips out of them. And then in the early 80s, which is when Lam was formed, that was about when most of the other equipment companies were formed. It was often from people, engineers from like Intel that like, hey, you know, I could do this better. I'm gonna start a company to do this. So, you know, that's really where our core strength is understanding the materials and the processes and building the equipment. You know, we have no desire to go in and run a fab. That's a different set of core strengths.
I see, thank you.
Good point.
Yeah.
Very good point. Any other questions? Okay, maybe the last question is why, you stayed in Lam for so long, and what are the fun things you do, make you so excited, and do you want to continue to work for Lam, so hopefully some of our students will get excited and want to apply to Lam.
Yeah, I've stayed for so long because I've gotten to do so many different things. Originally as an engineer, I get to work on all kinds of different materials and processes. I get to, I've been able to do atomic layer deposition of like metals and metal nitrides, and then work on, different types of CVD processes to deposit dielectric materials. And then also had an opportunity to do different business roles and have, different impact on the company. So, I like that process of figuring out, hey, what do we not know how to do yet, or what could we optimize, and let's figure out how to do it. I always used to describe my role as an engineer as probably like 80% problem solving and 20% communicating what we learned about how we solve the problem.